Hey folks, welcome to my channel Number Pen. So there we have the problem on the screen. Integrate the following with respect to x. We have root of x square minus a square, right? So what we've been given is dy by dx and we've been asked to find y. My y is nothing but integral of the given expression. So let's write down what our y is. So that's my y, integral of square root of x square minus a square times dx. I know that my y is not in a very simple format whose antiderivative I know from first principles. But then when I take a closer look at y, I see that I have a quadratic expression whose coefficient of x is 0, right? So we have an x square minus a square. So we have an x square term, we have a constant term, both sitting inside the square root. So, which means I can solve this directly by the method of trigonometric substitution, right? So the point here is figuring out what is the best possible substitution. And it looks like we have to make the substitution x equals a secant theta, right? Why is that? Because my secant squared theta minus tan squared theta equals 1. And when I make the substitution x equals a secant theta inside my ax square minus a square, what happens is my square root term, or rather the term inside the square root, becomes an a square times secant square theta minus 1, which is nothing but your a square times tan square theta, right? But then before that, let's work out our dx as well. What's our dx? When my x is equal to a secant theta, my dx is equal to a times secant theta tan theta d theta, right? Let's go back to our y and let's make the substitution represent everything in terms of theta, and let's see if we are able to simplify what we have. So my first part, which is a square root of x square minus a square, we already discussed, and that becomes an a times tan theta, right? Because my secant square theta minus 1 equals tan square theta. And then I have a dx component as well, which means I have a times secant theta tan theta d theta. So I have a double a in the expression, which means I can take out a square, which is a constant. I can take it out of the integral. What happens to the remaining portion of the expression is I get a secant theta times tan square theta, right? And then I have my d theta as well, right? So now I'm going to park y aside. So the job in hand is to solve for integral of secant theta tan square theta d theta, right? So how do we go about solving this? So if I assume my integral of secant theta tan square theta d theta is of the form integral of u dv, right? Can we solve this using integral by parts? So if I express my integral of secant theta tan square theta d theta, if I draw a parallel to integral of u dv, what is the right u and v in this particular expression, right? Let's assume that my u equals tan theta, right? And my dv equals secant theta tan theta d theta, right? Why is that? By this time, you folks must be familiar with why I made this particular substitution, right? Because I know that when dv equals secant theta tan theta d theta, my v is quite simple. It is again a secant theta, right? And then when my u equals tan theta, my du becomes secant squared theta d theta, right? So now what happens? I apply integration by parts, right? And what does my integration by parts tell me? My integral of u dv equals uv minus integral of v du, right? So I have my u, I have my v, I have my du, I have my dv as well, right? So what happens to the first part, which is my uv, becomes a secant theta tan theta, and then I have a minus of integral of v du, right? And what is my v? My v is secant theta, and my du is secant squared theta d theta, right? So what is my secant squared theta? It's nothing but a 1 plus tan square theta, right? I hope you folks are with me. So what we are actually doing is we have an integral of secant theta tan square theta d theta on our LHS, and on our RHS we have a secant theta tan theta minus integral of secant theta into secant square theta d theta, right? So actually it is a secant cube theta d theta, but I want you folks to watch this out very closely. So what I do in the next line is I go to my next line, I still have my LHS, right? Which is integral of secant theta into tan square theta d theta. My first part remains as it is, okay? Secant theta tan theta. And my second part, what I do is instead of writing this as secant cube theta, which is going to make my problem more complex, what I do is I retain the secant theta, and instead I express my secant square theta as 1 plus tan square theta, right? Now what we are going to see in the subsequent step will tell you why integral calculus is always super interesting, right? So integral of secant theta tan square theta d theta, if I call this as I, for example, so my first part of my RHS remains secant theta tan theta, and then my second part becomes integral of, I'm using the sum rule of integration here, integral of secant theta, that's part 1, okay? I have my d theta, of course, and then I have minus of, take a close look at this, I have minus of integral of secant theta tan square theta d theta. And what is that? That is nothing but it is again your I, right? It is nothing but your LHS, right? Let me highlight this, right? So now what happens is I have my I on the LHS, I have a minus I on the RHS, right? So I can move the I on the right hand side to the left, call it 2I, and I have a secant theta tan theta minus integral of secant theta d theta. I'm sure by this time all you folks are quite familiar with this now, and I want you to remember this by heart, right? Log of secant theta plus tan theta, and then I have my constant plus c, right? So now I have an expression for 2I. I need my I from this. It's not too difficult. What is my I? It's a 1 by 2 times the expression what we have, right? And like we do in many of our problems, we will have to put back everything in terms of x, right? And I'm not going to do it here, right? So this is our y, right? And now when you take a closer look, we have a square into secant theta, a square into integral of secant theta tan square theta d theta. So I'll have an a square times I, right? And what is our I? We just worked that out now. So that's my y. I can combine the a square and the half, and I can write this as a square by 2, right? Now I'll have to put back everything in terms of x. not very complicated for us. I have y equals a square by 2 times. So remember, what is that substitution that we made? The substitution that we made is x equals a secant theta, right? I'm just highlighting it out here for you folks. This is the substitution that we made. So what happens to the first part? I have a secant theta tan theta. My secant theta is nothing but an x by a, right? And what happens to my tan theta? My tan theta is a square root of secant square theta minus 1, right? So I have a square root of x by a the whole square minus 1. Now that's my part 1, and I come to my part 2, which is nothing but a log of mod of, again we have a secant theta, which means I have an x by a, and then again we have a tan theta, which means I have a square root of x by a the whole square minus 1, right? So that's my answer to this problem, and I do see that there is an opportunity to further simplify this. Reason being, the first part of the expression, if I take the a square inside the bracket, right, what happens is I'll be able to cancel out the a square in the numerator and I'll have an a square in the denominator as well. So I'll be left with an x by 2 here times square root of x square minus a square. Okay, and then I come to my part 2, and when I combine the a square by 2 expression with the part 2 log expression, I get a minus a square by 2 log of mod of x plus square root of x square minus a square, the whole divided by a close mod. So that's our y, and looks like we have some further simplification to do. Because when I look at the second expression, I see that the expression is of the type log of a by b, and I know very well that my log a by b equals log a minus log b. So I'm going to use that quotient formula of logarithms and rewrite this as, so my a square by 2 times log of mod a is nothing but, it is again a constant, right? So I can combine this entire expression and maybe call it C1, right? Which is again a constant. So let's finalize our answer to y. My y equals, so that's my y, x by 2 times square root of x square minus a square by 2 log of mod of x plus square root of x square minus a square plus my constant C1, right? So let me highlight my final answer in pink. And there we are. I hope you found my content useful. Please do subscribe to my channel and support. Thank you.